So finally, 9.4 is all about three-dimensional vectors. And the takeaway from yesterday's idea was that the concepts in general of two-dimensional to three-dimensionals, there are a lot of similarities. We can take a lot of the ideas that were grounded in two dimensions and extend it to the third dimensions by just factoring in the extra z components. And guess what? That's going to be the same thing here. And so it's sort of like an anticlimactic conclusion that, hey, how do we do three-dimensional vectors? You do it identically to two-dimensional vectors, except, of course, you have three components. To prove it, notice we're going to do another comparison chart, like a t-table chart here. So on the left-hand side, we'll write down all the stuff we know about two-dimensional vectors. So what are some things that we know about two-dimensional vectors? What did I ask you guys to do in 9.1 and 9.2? One thing I asked you guys to do is find the components of a vector if I gave the initial and terminal point. So in two dimensions, we know that the component of a vector with initial point P, and it's some coordinates, let's call it x1 comma y1, and terminal point Q, it's going to be some point x sub 2 comma y sub 2, is, and you always do the terminal minus the initial, so it's x sub 2 minus x sub 1 comma y sub 2 minus y sub 1. Not surprisingly, the concept in three dimensions is going to be super duper similar, except we have a third component, a z component. The component of a vector with initial point P, x sub 1, y sub 1, but since we're in the third dimensions, it has a z sub 1, and terminal point Q, x sub 2, y sub 2, z sub 2, is, not surprisingly, the same concept. Terminal point minus the initial point. X sub 2 minus x sub 1, y sub 2 minus y sub 1, except you have a third component, z sub 2 minus z sub 1. So it should not be a groundbreaking new thing. It's just extending what you already know to the third dimensions. What other things that I have you guys do in two dimensions is magnitudes, right? So we should be able to find the magnitude of a vector if I give you its component form. So if you have vector u that has components x comma y, then we should know the formula for the magnitude, right? That's just the square root of the horizontal component plus the vertical component. Not surprisingly, in three dimensions, if you have a vector that's in three dimensions, x comma y comma z, then its magnitude is simply x squared plus y squared plus z squared square rooted. So it's the same concept extended to the third dimensions. We also talked about adding and subtracting vectors, right? If you have vector u in component form, let's call it ux comma uy, and vector v in component form, vx, vy, then to add these two vectors, you just add the x's, add the y's. Ux plus vx, uy plus vy. And then same thing for subtraction, etc., etc., etc. Right? I'm not going to bother writing the subtraction part. Well, guess what? It's the same thing for three dimensions. If you have a vector, a three-dimensional vector, ux, uy, uz, and vector v, vx, vy, vz, then if you want to add them up, just add their components. Ux plus vx, uy plus vy, uz plus vz. And again, same thing for subtraction, etc., etc., etc. So, I mean, I'm sort of like taking this lightly, but in terms of the math behind it, it's nothing new really. It's pretty similar and straightforward. The only thing that is the same is, well, actually, let me talk about, there's one other difference. It's just a slight difference. It's just a notational difference here. Um, so we know that there are three various forms to represent vectors in two dimensions, right? You could represent vector u in the angle bracket notation, in the stack column notation, or in the I and j notation. That's what I really want to talk about. Same thing for three dimensions. If you have three components, x, y, z, stack notation, x, y, z, and then you have x sub I plus y sub j. The unit vector in the z direction, they just, technically you can use whatever letter you want, but mathematicians like to go in alphabetical order. The unit vector in the z direction is typically k, right? So just be mindful of that notation. But the one thing that is very translatable is the dot product. So the dot product is a scalar product. It sort of measures how close two vectors are pointing in the same direction. So in two dimensions, we know that if vector u is x, u sub x, comma, u sub y, vector v is v sub x, v sub y, then what is the dot product? That is simply ux times vx plus uy times vy. Basically, x times x plus y times y. Not surprisingly, it translates nicely into three dimensions. If x is u sub x, u sub y, u sub z, v sub x, v sub y, v sub z, then the dot product is just multiply the x's, multiply the y's, and multiply the z's, and then just add them up. ux, vx, plus uy, vy, plus uz, vz. So that's really the only difference there. However, whether or not it is two dimensions or three dimensions, they both share one common formula, and that's the angle between two vectors. Right? Angle between two vectors, because it doesn't matter if I'm dealing with two-dimensional vectors or three-dimensional vectors. If I'm only looking at the angle between two vectors, it's going to be, the same no matter what, the same concept. So if two vectors u and v are have an angle theta between them, then then the cosine of the angle between them is equal to the dot product divided by the magnitude of one angle times the magnitude of the other angle. Right? So that, regardless of what dimensions you're in, that is going to be the same. So, like I said, it's sort of an anticlimactic lesson. It's everything that we've learned in 9.1 and 9.2 translates nicely into the third dimension. It's just you have to factor in the third component. So because of that, I'm going to sort of like take a leap of faith here. I'm not going to do any examples. Let's see whether or not we can apply what we've learned in two dimensions to the third dimension. So your practice has the answer key, so you can check your answers, but give it a shot on your own. Let's walk in blind. Can you use what you already know to this, quote, new system? And of course, I'm always here to help you if you get stuck or something. So if you are trying this on your own and it's not working, please reach out to me and I'll help you as best as I can. So that is it. That is 9.4. Those are three-dimensional vectors, the math behind it anyway. So good luck.